So I pressed the magic go live button and we are now live on YouTube. We'll just give another minute and then we'll start. Okay, so perhaps I will do an introduction if you're ready, Nancy.
Sure.
Great. I am so excited to introduce Nancy J. Cooke, who is a professor of human systems engineering at Arizona State University, where she directs the Center for Human, AI, and Robot Teaming and the Advanced Distributed Learning DoD Partnership Lab. So just to highlight a few things from her really impressive bio, she received her PhD in cognitive psychology from New Mexico State University. Dr. Cooke is a past president of the Human Factors and Ergonomics, and she recently chaired a study panel for the National Academies on enhancing the effectiveness of team science. She was also a member of the U.S. Air Force Scientific Advisory Board from 2008 to 2012. And her broad research interests include the study of individual and team cognition, human-robot teaming, cybersecurity, intelligence analysis, remote piloting aircraft systems, healthcare systems, and emergency response systems. And her talk today is about ASU Center for Human Artificial Intelligence and Robot Teaming. So welcome to the seminar, and we're really excited to have you here.
Thank you very much, Stacy. I'm really happy to be here. I want to keep this as interactive as possible over Zoom. So if you have any questions, feel free to jump in and unmute yourself. I'm going to tell you today about the center that I'm directing, which was stood up in February of 2017. It's called CHART, the Center for Human Artificial Intelligence and Robot Teaming. And it is a center under the umbrella of the Global Security Initiative, which is a knowledge enterprise initiative. First, let me back up to some of my background and how I sort of found myself in this place. I am a cognitive psychologist by training, but I've always done applied cognitive psychology, cognitive science. And I started out being interested in individuals and individual cognition and individual expertise. But then about 25 years ago, a person who's a leader in the team area, Eduardo Salas, said that they understood that team cognition had been, or teams really, had been a part of industrial organizational psychology and had been studied for a while there, but that after the Vincennes incident, where the US ship brought down an Iranian Airbus that was full of civilians, by mistake, and this was supposedly due to some really bad teamwork and team decision-making under stress. They decided that there needs to be more cognition into the teamwork area. And so he said, you know, you study individual cognition, let's see what we can do with teams. And I've been working on this problem of team cognition ever since. I study team cognition in pretty elaborate socio-technical systems, so systems where there's lots of technology and lots of people. So like NASA mission control or incident command, emergency response, hospitals. But in general, I studied the cognitive processing of teams in this context, and my goal is to overall improve team effectiveness. Some of the teams and most of the teams that I have studied are action-oriented teams. These are teams that quickly have to produce some kind of action. They have to coordinate usually very quickly in order to do so. These teams include teams that control remotely piloted aircraft systems, such as the Air Force Predator system, shown in the left upper corner, sports teams, medic teams, hospital teams, such as Code Blue resuscitation teams, and nuclear power plant teams are some teams that I studied. I've done a little bit with decision-making teams too. These are teams that come together and spend a little bit longer time coming to plans, making decisions as a team. And I think it's important for the way I think about team cognition to separate action teams from decision-making teams. I'll talk about that later, but these include teams like incident command teams, cybersecurity teams, intelligence analysis teams, and non-combatant evacuation operation teams. So they're basically planning and decision-making teams. But more recently, I've been studying a different kind of team, human autonomy teams. Let me go back, hold on. These are teams that are made up of, they're heterogeneous teams made up of multiple individuals, some of them human, some of them not. They could be embodied AI or robots, or they could just be an artificial intelligent agent. So this is the kind of teaming that I've been studying most recently. And a lot of people are interested in this now, especially in the DoD. We see lots of examples where they want to have multiple humans working with robots, working with wearable AI sensors and AI systems in general. So I'll be focusing most of the talk on these kinds of teams. And that's where CHART comes into play. So this is a Center for Human Artificial Intelligence or Robot Teaming. And I think one of the important things about CHART is that we put humans at the center of all of this. So we have, we say, for instance, technology teaming with humans for global security, not humans teaming with technology. We think the burden should be on the technology and not on the human. The human should not have to adapt to the robot should adapt to the human. And so what we look at, we believe firmly that the coordination of teams, these kind of heterogeneous teams composed of multiple humans and artificial or synthetic agents, is critically important. And our mission is to assemble across the university and also external to the university, multidisciplinary teams to address these human-machine integration issues in various application areas. Because we're under Global Security Initiative, a lot of the application is in defense, but also we define security very broadly at the Global Security Initiative. And so we consider transportation, emergency response, manufacturing, and medicine as all related to security. So I'm the center director. They put me together with Spring Berman, who's the center associate director. Spring is in SEMTE in the Fulton Schools of Engineering, and she's a swarm roboticist. So it's kind of an interesting combination of someone who knew about human teams and someone who knew about robot teams coming together to lead the center on human and robot teams. We have a lot of faculty that we're working with. Dr. Li Xiao Wang is a research scientist for our center. And we have, what's notable about this is that we have 60+ faculty across very many disciplines. And some of them are disciplines that you would expect, like engineering and robotics, but others you might not, like law, ethics, arts, which I think is relevant to what you do. And we really do come together and solve problems together in this interdisciplinary way. And to me, that's very rewarding. So there are a couple things I think that are really important to do this kind of research. I don't think that you can do research in the lab on human AI robot teams without having test beds and without using the Wizard of Oz paradigm. I'll show you some examples of test beds, but basically by test bed, I mean a simulation that we concoct in the laboratory that simulates real world tasks and allows people and robots to exercise the same kinds of collaboration that they would in the real world, but it's now in a lab and so easier to control. It's sort of a compromise between field research that's very difficult to control and really simplistic laboratory research that is doesn't really scale up to the real world, it has little external validity. Now the Wizard of Oz paradigm is interesting. It comes from the Wizard of Oz movie, which is one of my favorite all-time movies, where you have the wizard behind the screen, and the quote, "Don't pay any attention to that little man behind the screen." So in the case of this kind of research, we often use the Wizard of Oz technique to simulate the behavior of a robot or an AI agent. So that means that a human behind the screen plays the role of the AI agent or robot, or operates the robot. And so this way, we can test all kinds of different robot responses, robot explanations, AI communications with humans. We can do a lot of what-if testing without having to develop the AI and the robot in like 10 different configurations and then test them only to find out that maybe only one of them was any good. So it speeds up this work tremendously. Okay, so we're back to, we conduct research on these real world tasks, and in order to do that, we usually go out to the real world and try to understand what people are doing in the real world. What are their challenges, especially as a team? Are they working with technology? What are those challenges? And then we take that environment and bring it into the lab. So we've done this in my lab in a number of different ways, and I'll show you more about these, but we have a generic team decision-making environment in which we've studied, simulated non-combatant evacuation operations, cybersecurity, either done by individuals or teams, intelligence analysis, and most recently we're getting ready to do a DARPA project in which we use Minecraft, as you see here also on the slide, to simulate a collapsed office building and to do urban search and rescue kinds of human-robot interaction tasks. And we've simulated what medics do by having both a cognitive and physical team obstacle course in our lab. And the one that has been used the most is the one in the upper right, which is a remotely piloted aircraft systems synthetic task environment. That is a 3-agent task, and I'll give you some more information about it later, but we've been studying it for since 2000, so 20 years now, and have learned a lot about teams, and now we have a synthetic agent that we have inserted into the pilot seat of that task, and we're learning a lot about human AI teams. So here are the objectives of the various research programs I'm going to tell you about. We develop realistic research test beds for both empirical and controlled human-in-the-loop studies. And we develop real-time, unobtrusive, systems-level dynamical measures and models. So we really focus a lot on measurement. We firmly believe that if you don't understand it, you can't measure it. And if you can't measure it, you can't improve it. And so we focus on trying to develop measures of kind of hard to measure things like coordination. How do you measure team coordination? And even harder than that, how do you really measure team effectiveness? We've been working on that, focusing on that lately. We also try to gain a theoretical understanding of team cognition. We've, based on all of the data that we've collected, developed a theory called interactive team cognition, which proposes that team cognition is not so much inside the head of the individuals, but really emerges through their interactions with each other. And then we use our empirical findings as guidelines for robot agent development. And to give you an example of that, I'm working with Rao Kempempati, and some of the work that we do in our lab using Wizard of Oz techniques, looking at robot explanations and the type of explanations that are given to the person in the Minecraft environment. Which ones of those work the best, we feed that information back to him so he can use it for his robot planning algorithms. Our desire is to improve human-machine team performance or team effectiveness, not by teaching humans how to work with these machines, but by designing machines to be good teammates. Again, the onus should be on the machine, not on us. In our, I'm going to talk now about projects, and these are projects out of my lab, and I have collaborated with lots of people across the university on these projects, but I don't want to give the impression that these are the only projects going on under the chart umbrella. These are just the ones that I'm closest to. But there's a lot of, since we stood up CHART, there's been a large growth in research in this area in the university. And those are my dogs barking at the FedEx truck. So let me talk about human robot teaming for urban search and rescue. And we have a project that is funded by AFOSR to look at this. And we also just started a big DARPA project to look at this. I'm going to tell you about the AFOSR project, but just to give you a little bit of insight into the DARPA project, what we are doing is we are empirically evaluating in a Minecraft context the performance of agents that are developed to help an individual or a team search for victims in this Minecraft environment. There's other performers that are coming up with hypotheses about individuals and teams in this search environment. But all of these performers, and there's about 150 of them, will convene at, well, if we can ever convene again, they'll convene at ASU several times a year in order to have their agents tested. And I always say, I think, how cool is it that ASU is testing agents developed by MIT and Carnegie Mellon? I think it can't get any cooler than that. Let me tell you about the objectives of the AFOSR program. So, and this is the program that I'm doing with RAU, and it focuses on the development of robot teammates that can effectively team with human operators in victim identification and triage. And we're looking at how does a type of explanation, and now we're looking at also transparency provided by the robot, how can it affect the outcome or the performance of the human, as well as the trust and situation awareness of the human participant. And to give you an idea of what they're doing, let me show you some pictures here. So we have, this is Wizard of Oz. So we have on one side, on the right side here, the person who's playing the role of the robot who actually is in the Minecraft environment looking for victims. And then on another side, or actually in another room, we have the operator whose task it is to map, to mark on a physical map the location of victims in that building, with the idea that people will come in and triage them and rescue them later. And so this creates a lot of need for interaction between the robot and the human, because the human only can see, if you see this is the, well, these are both humans, but this is the human that's actually playing the human and is actually a random participant looking at a camera view from the robot that's inside the building. So they have a restricted view, but in addition, the building is collapsed. So there's going to be openings where there didn't used to be, or where they're not indicated on the map. And there's also collapses that aren't indicated on the map. And so there's a lot of questions, so there should be a lot of questions that the person who's marking on the map asks of the robot, like, why did you just walk through the wall, kind of thing. And it creates the need for explanations and transparency. Okay, so we're in the midst of doing that, as well as starting up on our DARPA program. But this project, or the Synthetic Teammate project, has been work that's been done since the year 2000, first supported by, well, we're working with the Air Force Research Lab. They're the actual builders of the Synthetic Teammate, and our work is funded by Office of Naval Research. Our objectives of this project are to develop a synthetic teammate to take the place of the air vehicle operator or pilot and work with two other humans who are the sensor operator or photographer and the navigator in a remotely piloted aircraft system testbed. So the testbed both provides a validation environment for the synthetic teammate in which we can compare the performance of teams with a synthetic teammate on them to all human team baseline data. So just a little bit of background about this. Why does AFRL want to do this? The reason that they're doing this is because right now the training, to get team training, requires lots of people's time and money. They do live virtual constructive exercises where sometimes there's hundreds of people, many of whom do not need training themselves, but they're just serving as sort of nodes in this big network of people who are working together as a team. They are reasoning, AFRL, that if you could make synthetic teammates to stand in for these hundreds of people who don't need training, that I, who need training, team training, could go and get my team training with these synthetic agents on the internet anytime, anywhere. And probably this is the way, seems to be the way we're moving in general. They also were interested in the actual modeling of the synthetic teammates. So they've made this the largest ACTAR cognitive modeling architecture in the world. They really stretched that capability. And we were interested in this project because we wanted to see how good of a team player would the synthetic teammate be. And just to give you, well, I'll get to this in a minute, but it was kind of like a test of what are the essential features that are required to be a good teammate. We knew that you have to understand how to do your task, how to be a pilot or sensor operator, but what else? And we thought it was going to be more, so natural language understanding was a hard nut to crack in this project, but we thought that it would be, there would be other things that would be also important in being a good teammate, like understanding the essentials of coordination. And just to show you a little snippet of data, we have 3 conditions here. The synthetic condition, which is the red line, is a condition where you have 3 teammates. One of them is the synthetic teammate and the other 2 are human. Control condition is the all human baseline. An experimenter condition was a condition in which we put a well-trained experimenter, graduate student or postdoc, in the seat of the synthetic agent or the pilot, in the seat of the pilot, and they actually tried to coach coordination. So in this task, coordination means getting the right information to the right person at the right time when you get to one of these target waypoints. Everything happens at a target that you have to photograph. And the 3 individuals have to carefully get information to the right person at the right time. Well, you can see that the synthetic teammate teams didn't do as well as the others, and over time got even worse. What's interesting here is what happened is that the synthetic teammate was pretty good at doing its task, but it acted like there were no other individuals on the team. It was pretty selfish. It did not provide information to other teammates unless they asked for it. People in this task over time, well, people come to the task knowing what it means to be a team member, knowing that you probably need to give people some information. And so they learn over time that, yeah, you need this, I'm going to give it to you at this particular time. The synthetic teammate did not do that. Now, why did the synthetic teammates get so bad? Well, over time, and this is kind of scary to me, we have not a terrible synthetic teammate, but it was just kind of a selfish one. And over time, the humans on that team entrained after the synthetic teammate and also became more selfish. So everybody's just waiting to be asked for information, and coordination suffers. On the other hand, in the experimenter condition, those teams were solid and did well the whole time because the experimenter kept prompting people for the information needed, and as a result, kind of trained the team, the other 2 people on the team, how to do this coordination in an effective manner. So I think these results show how one team member, synthetic or otherwise, can either bring a team down or lift a team up on a 3-person command and control team. And we were getting ready to test a revised version, updated version of the synthetic teammate. Right after spring break, we were going to start doing that. But this is one of those experiments. It's really hard to do remotely, so it's on hold for a minute. Not a minute, probably longer. Okay, here's another one, a test bed that is underway, almost completed. This is for the area of transportation and specifically driverless cars. We're developing a test bed that's capable of simulating conditions similar to those experienced by full-size autonomous vehicles when they're on the road with human-driven vehicles. So we're asking about interactions between drivers in cars and autonomous vehicles. This is a situation that you see, for instance, in Tempe. Often we have autonomous, not anymore, Uber drivers or Waymo driving around. And how do people interface with those vehicles? Not just people who are pedestrians or cyclists, but also people in their cars. For instance, there's been reports that autonomous vehicles often get rear-ended at a stoplight as it's turning yellow. That is because they stop and the person behind them keeps speeding up. That's what we do. We speed up, they stop, they get rear-ended. So we're interested in those kinds of interactions and how people behave, how it changes their behavior if they know or don't know that a vehicle is autonomous. So we have these research questions that we're asking about people's, basically their attitudes and behaviors in the presence of autonomous vehicles. And to do this, we are developing a test bed. And this is a real good example of one of these really nice interdisciplinary collaborations where Spring Berman's group, who does swarm robotics, has developed vehicles that we're calling GoCharts. So Chart's the name of the center, Chartopolis is the name of this test bed, and GoCharts are the name of the cars that she's developing to drive around autonomously in this town called Chartopolis. Human-driven cars will have to interact with the driverless cars. So some of these cars won't be autonomous, but will be driven by humans in a simulator. And this will be situated in a modern urban setting. Now, here's something really cool. We're working with Lance Garavi from ASU's School of Film, Dance, and Theater. And this is the latest version of Chartopolis. So he's an artist, and you can see here, I think there's a little Go chart down here on the road that can drive around. This is his Chartopolis, or he calls it Robotopolis, but it is not, to him, only a test bed for research. So we're not only going to do research in here, but he considers it an art installation. He's developed it to be like an architectural 3D model. And he calls this the, so this is the future where we have robots driving around in our streets. And interestingly, he uses light, and the light changes over the day as if the sun's rising and setting, and casts shadows on the ground here that do not map onto the actual structures. And he talks about this as these are the shadows of what used to be this city. And you can, I don't think you could see it in this picture, but maybe you can. There's some shadows of trees that are no longer there. So this is kind of a sad, a little bit sad thing. The whole place has changed. So it's been a really rewarding experience working with Lance and Spring and their students on this project. And I think it's going to be really amazing when we're finished and able to collect data. Right now, they're putting up stop signs and stoplights and things. Okay, here's another project. We're looking with the Army Research Lab at future combat vehicle concepts. And this is a project that a lot of people in the Army are interested in now. It's about having a platoon that involves 2 manned tanks, each of them with 7 people in it. That's what these manned combat vehicles, MCVC, MCVF, and then each of those have 2 wingman vehicles, remote combat vehicle A, remote combat vehicle B, that are unmanned and that are controlled by people in this vehicle. Even in front of them, the concept is that you would have UAVs going out in front. You can imagine that this creates a lot of communication and collaboration issues, not only in here in the tank with all the 7 people in it, each doing something different, but between the people and the remote vehicles and the UAVs. And so we've been asked to look at concepts of collaboration and interaction within this setting. And so we're looking at interactions. What are the possible interactions? How can they work? How can we measure them? How can we design interactions and design the task so we can decrease workload, increase situational awareness, and increase performance? We have developed an interaction taxonomy. What are the different ways, different modalities with which people can interact with each other and with technology? And how does communication flow in particular tasks? We are now in the middle of building some test beds. We're also building metrics and modeling techniques. And most of these techniques use communication data to try to say something about team trust. So can you, based on how teams are communicating, get some indication of trust or situation awareness or workload? And so we're developing some novel measures in that area. The test bed that we're developing, we have 2 test beds we're developing. One is going to use Chartopolis, so it's more of a physical test bed. And the other's lower, well, they're both pretty low fidelity. The other is using Minecraft to build a battlefield with tanks moving around on it. And then this can get awfully big because right now, currently, we're just developing our measures and test beds based on the Platoon level. But you can imagine as this gets bigger, the interaction network becomes much more complex. So we're always thinking about scale as well. Okay, one more project that's probably not as clearly fitting under the chart center. It's a NASA project for sensing and monitoring human performance in the national airspace for risk prediction. The PI on this is Youngming Liu, also in Fulton School of Engineering. And we're working with a lot of people within Fulton and also outside ASU to do this project. And basically the idea is that there's lots of data out there that we can collect in real time about weather, about air traffic density, about the airplanes themselves, to in real time, using lots of machine learning algorithms, say something about risk in the national airspace. Our part of this job is to take data from the humans, air traffic controllers and pilots, to go into this huge equation to say something about risk in the national airspace. And so we're looking at how human factors interact with other factors in the national airspace to affect the air traffic controller performance. To do this, we're thinking about communication as an index of collaboration. We think it's very rich. There's lots of communication you can look at, and you can collect it automatically and in real time as air traffic controllers are communicating with pilots. We have developed a simulation at the Polytechnic campus in the sim building. We're using their TRACON or radar simulation room. We're bringing in retired air traffic controllers into the lab. We've had 6 of them in so far before coronavirus. And we measure various signals, including communication, over time as we ramp up air traffic density, as we introduce perturbations and things that are going wrong, runway changes, for instance, trying to actually break the air traffic controllers to see what that looks like in terms of all of these indices that we're taking in. And these are some pictures of the simulator. By now we've had 6 retired controllers in, and we're looking at, and we have pseudo pilots. Those are students who play the role of the pilot, and sometimes they're controlling 3 or 4 planes at a time, so that we can ramp up the workload. We find that there are certain kinds of signals that we're getting that map onto loss of separation, which is when planes come dangerously close to one another. We don't want that to happen, but we can, in these scenarios, see that that does happen when there's workload, when there's multiple things going wrong. And then we can see how that looks in terms of the communication patterns, with the idea being that we'll say, if we see these communication patterns in real air traffic controllers, we will that will signal that something may be wrong. We are looking at things like biometric heart rate variability, facial expression as well, although we know that we probably won't be getting these things in in reality, we'll only have communication data, but we want to see how they map onto the communication data to give us some cross-validation. And this is just some of our data showing increased loss of separation over time in a scenario. This was a high workload scenario that ramps up from just like a few planes to about 16 planes. And so you get increasing loss of separation as you ramp up the traffic density. All right, so that is it for the projects. I just wanted to switch to sort of a summary of what I've been thinking about in this area of human autonomy teams, and thinking about it from the perspective of what I know about human teams. And if you really take the word teaming seriously in human autonomy teams, we've done, there's been a lot of work in the field in human-robot interaction. And that's really one human, one robot, looking at their interaction. But we're talking about something different now in a team. And a team, by definition, have members that have different roles and responsibilities. If you don't, you just have a group. So a team's a special kind of group that has different roles and responsibilities. And I think what's really critical there in terms of human autonomy teaming is that one thing that we really don't want to do, for the most part, is to replicate humans in robots. I mean, I know we have humanoid robots that might be okay for some social applications, although I'm not quite so sure that they're working well. But for the most part, we want the robots and AI to do the things that we either can't do or don't want to do because they're dull, dirty, or dangerous for us. That should be the job of the robot, and we should do what we do best. I mean, I say we already know how to replicate ourselves. We can do that really well, but we can't do everything well. So we need the robots and the AI to help us do the things that we can't or don't want to do. Now, this kind of flies in the face of our synthetic teammate experiment. I think that's an application where you do want to replicate humans because you're trying to provide people the type of training that they would get if they were training with humans. But for the most part, I don't think we want to do that. Also, effective teams understand that each team member has different roles and responsibilities. And they avoid role confusion, but back each other up as necessary. Now, the two things that happen with human teams most often that make the team ineffective, and you might have had experience being on a team that wasn't so good. I know I have, and I've seen them, even in my lab that studies teams, we see examples of teams that aren't so good. Two things that go wrong: poor communication and role confusion. Role confusion, poor communication, I think is pretty straightforward. You just don't communicate clearly or accurately, or when you should. Role confusion is when you don't, I thought you were going to do that. No, I thought it was your job. And so people get confused about who's doing what, and that leads to usually team breakdown. The synthetic teammate really didn't do very well at this. It didn't really understand what each team member had to do. And I think this argues for autonomy needing a better understanding of the whole task. Now, in the case of the synthetic teammate, a lot of people, when I present that research, they'll ask if what the synthetic teammate is missing is a theory of mind. And this is exactly what we're looking at in the DARPA project, social intelligence and the need to have theory of mind. I actually think that that theory of mind, at least for the tasks that I've been doing, is a bit of overkill. I think all the synthetic teammate needs to know is how this task works from the team perspective. It doesn't need to know how the human's feeling that day or what the particular strengths of that individual are. I think it really just needs to understand the whole task. I think this goes along with the idea of replicating humans. Sometimes we spend a lot of time trying to program things like theory of mind, when if we think about robots and AI as a different species, it may be that they don't need to have that. They don't need to be exactly like us. Now, the next thing is that effective teams share knowledge about the team goals and the current situation, and this facilitates coordination and implicit communication. And usually it's very rare that you can put a team together and they work effectively from time one. Now we do have ad hoc teams, and I've done some research on code blue resuscitation teams that come together and maybe have never worked together on a team. Well, that presents challenges for the team, and those are the kind of challenges that we look at. But for the most part, teams get better when they work together, and the longer they're together, the better they become. So this suggests that human autonomy teams also need training and time to work together. I often think about human autonomy teams and the analog human-animal teams. So bomb-sniffing dogs or cadaver dogs. These human-animal teams are very, very effective, very good at what they do. They only do one specific thing, and they've trained together extensively. And I think that's a lesson that we should learn about human autonomy teaming. Effective teams have team members who are interdependent, and they need to interact and communicate even when direct communication is impossible. I think that we also put a lot of effort in natural language understanding with autonomy. I mean, we talk to Alexa and Echo, and is that really necessary? Are we just, is that overkill? And I think in many cases, yes. Taking human and dog teams, for example, they don't speak in natural language, but they get the job done by virtue of lots of training together, and also a different kind of language, more like signaling. And so I think sometimes we would be better off if we did this kind of signaling with robots. Again, thinking of them as not like us, but a different species that we have to interact with differently. And finally, interpersonal trust is important to human teams. And so this suggests that autonomy needs to explain, be explicable, be as transparent as possible. We've seen examples where people will stop trusting it or they overtrust it. The Boeing 737 MAX 8 is an example of that. So trust is important, and I think that's one of the harder nuts to crack here. Okay, and that's it. I just want to acknowledge that there's been an awful lot of people who have helped on these different projects, both other faculty and postdocs and students, and many people. There's other labs too. So I just want to say thank you. And if you're interested in working with CHART, we really welcome collaboration in any of these areas. We like to do multidisciplinary research. We at times put on workshops or conferences. And we also like to work across not only other academic institutions, but government, industry, military. So thank you very much for your attention, and I'll take questions.
Thank you so much for that lovely talk. I will be monitoring the comments. So if the folks watching on YouTube, if they ask anything in the live chat, I will report that back to you. And for the folks in the Zoom, feel free to either raise your hand or type something in the chat. And see that Caroline has a question. I think you're raising your hand, Caroline. No, clapping. My apologies.
Virtual clapping, I love it.
I also tried to clap with the reaction. So maybe I'll ask a question first. So I'm curious about what you said about how, you know, the goal of these teams is not for the robots to replicate human actions and not to create these humanoid robots necessarily, which I think is fascinating. But I'm also curious how humans then communicate with robots, if the humans on the team are not engineers, or if they're not, you know, I mean, I guess what I'm wondering is, do you still think that there's some room for the robot to communicate as a human, to be part of a human team, so as not to require, you know, all the team members to be engineers?
Right, and that would go along with the part about let's let the robot come to us. We shouldn't have to go to the robot. And this goes along with another project that I didn't tell you about that I'm working with Sid Siddharth and Georgios Vanikos on the future of work. It's an NSF-sponsored project, and we're looking at, is this, first of all, is this the future of work? I personally think that this Zoom thing is now the future of work, or the current work, but is the future of work when humans are going to be working more and more with robots and AI? And if so, then what happens to that part of the workforce that has not been trained as a roboticist or as a computer scientist and yet needs to maintain and work with these agents? So we're looking at ways that that people can learn on the job how to work with robots. And yeah, I think the robot has to come to the human. I think we can use AI to kind of determine the skills and the missing skills of the human and even of the robot. So you put the right robot on the team, you put the right human on the team, and you train each of them in the skills that are missing. So we have a large team that's currently working on that now, but it's a good question.
Yeah, thank you so much. Just to read back in the live chat on YouTube, Ozzy says thank you. So thank you very much. And also Patrick says very interesting on YouTube as well. And looks like Byron has a question. So I've unmuted Byron.
Great. Thank you. That was a really interesting talk. I think this approach to having the robots and the artificial intelligence adapt to humans is absolutely the right approach. In our digital culture program, which is our undergraduate arts, media, and engineering program, we teach a class called computational thinking, where we try to get students to understand sort of how computers, well, quote unquote, think. Basically, how do you think in those sort of terms, the syntax and communication with a computer? Do you think there is any role in this building teams in teaching humans to think like a robot or think like an artificial intelligence system?
Yeah, that's interesting. So that would be asking them to adapt more towards the robot. So I'm going back to my dog metaphor. When you have when you're interacting with a dog, trying to teach it tricks or train it, do you have to think like a dog? Maybe. I mean, I think it's good, certainly for humans to have expectations set accurately about what the robot can do, what it can't do, what the AI can do, what it can't do.
Maybe sort of how I'm thinking about this is that the dog is a great analogy, because you're not going to think like a dog. We don't know what it's like to think like a dog, but we should be able to empathize and to some degree and have an understanding of kind of the capabilities and limitations perhaps of the dog, to know that it's not going to collaborate like a human. So I don't know, it's more of a thought than a particular question. So
I think understanding the capabilities and limitations is very important, though. So we know the dog can maybe sniff for bombs, but it's not going to find fruit in somebody's luggage.
Yeah, that's great.
Great. So Diana looks like also has a question. So I'll try to unmute Diana.
Oh no, let's see. There, you did.
Yeah.
Thanks. That's so interesting. Several questions and thoughts arose as you were speaking, but I wanted to hear a little bit more about what you're learning, what we might learn from you on building resiliency and interpersonal or interagency trust building, especially now as we're adjusting to new modes of collaboration through Zoom, through our remote resiliency. How might you have lessons to guide us during this time around resiliency and trust building?
Yeah, good questions. And I think being distributed like this is a major factor in building trust and also in resilience. The more we have experience with either people or robots and AI, the more information we can take in to properly calibrate our trusts in various things they're going to do. So we're a little bit hindered by this technology and not being able to always see persons face-to-face, body movements, the context that they're in. So we're just being, we're limited, we're constrained by the amount of information that we can get to help us calibrate trust. So you might expect that trust isn't going to be as well calibrated. For resilience, I think we have done some work on team resilience, and that I think goes into the equation on team effectiveness. So we've been trying to figure out what makes an effective team. Most people in the team field look at effective teams as teams that produce good outcomes. So how many targets did you get good pictures of? How many cyber threats did you find? And in the lab, you can kind of measure that, but you can't measure that in the real world because we don't know what ground truth is. And also sometimes the outcomes, like recovering from a code blue resuscitation or cardiac arrest event, is not necessarily a sign of team effectiveness or ineffectiveness because there's other factors at play. So we've been trying to look at it differently and say team effectiveness, or an effective team, is an adaptive and a resilient team. And by that we mean an effective team is one that when there's some kind of roadblock or change in the environment that knocks it off its course, it quickly adapts to this change, but then over time rebounds and goes back to its resting place. And we do a lot of dynamical systems analysis to look at that. So we're trying to quantify what it means to be resilient in terms of the time to rebound. In this context, I'm not sure that we're talking about the same thing with resilience, but that's what I've done from the team perspective.
Thanks so much for that question and answer. And I also see that Pavan has his hand raised. So Pavan, I believe you should be able to.
Thank you. I mean, I sort of typed my question, but I can speak. And actually, the question was sort of partially answered by you in the previous one. I mean, I had a more of an engineering related question, which is, you know, the concepts you're looking at: team, trust, coordination, efficacy, resilience. And the data that you're measuring is so highly varied, everything from, you know, communications to affect to lots of other things. How much of, you know, when I see problems like this, I start going into rabbit holes about defining and measuring and validating each and every one of those to the desired levels of accuracy where you can start trusting those measures. How do you balance out all these competing, you know, points of attention? You know, you can go very deep into even one of those measures and spend a whole career trying to develop the right measures, right?
Right, and I think that's why I've ended up with this theory called interactive team cognition. So I think I'm a behaviorist at heart, even though I was trained in cognitive psychology and the information processing paradigm. People who started studying team cognition, the people who got me involved in it, were thinking of team cognition in terms of the knowledge inside the head and shared mental models. And do you have knowledge inside my head that's similar to knowledge inside your head? Great if it is. If it's not, then we have some problems being a team. And in my lab, I looked at that and it just didn't seem to be making sense. It didn't seem to matter if my knowledge was the same as somebody else's knowledge. What seemed to matter was the way that people were interacting. And to me, that I can get a firmer grasp on that because I can observe communication. I can observe interactions. I can't observe directly what's inside your head. So I think that's how I've approached it, looking at actual behavior and trying to say something about team effectiveness or trust that's all behaviorally based.
Great, thank you. Thank you.
Yeah, thanks so much. So we have time for one last question. And I see that Diana actually typed a follow-up question into the chat, which says, how does the importance of role clarity that you've identified allow for role fluidity and mobility, or does it?
That's a good question. In fact, I heard a DARPA talk recently where DARPA thinks that the way that war is going, the way that battle is going, is to what they're calling mosaic warfare. So it's different than having everybody has a role, or every machine has a role. And it's like a puzzle where you only fit into one place on the team or on a particular task, to mosaic warfare where people can morph and machines can morph, kind of like transformers. You can be in the water at one point and the air at another point, and people can switch roles. That's the way they think it's going. I don't agree with that. I think that the way it's going to work is that people and the machines have very specialized functions, much like the bomb sniffing dog, and we call them when we need them. So we assemble teams kind of on the fly based on these very specific roles. It's not to say that you don't have to have a little bit of breadth, like the synthetic teammate has to know a little bit at least about what else is going on in the team. But to expect people to be able to move from one role to another, sometimes very complex role, I think is a mistake.
Wonderful. Thank you so much for this great talk and the insightful question answer session. And with that, I think we'll wrap up and give you a virtual applause from our homes. And
Thank you. Thanks for having me talk to you. And I'm happy to get email questions if you want later.
Great. Thank you so much.
Sure. Bye-bye.